We are happy to have two presenters today. On the topic of supervised learning to prevent blackouts in power systems, and it will be jointly presented by Jochen Cremer, who just recently started as assistant professor at TU Delft, and by Federica Bellizio, who is PhD student at Imperial College and who is actually also a former ETH graduate. So I'm very happy to have you both here, and I'm looking forward to share your research results with you. So please also leave some time for discussions. And please, the floor is yours.
Thank you very much, Professor Fink. It's very nice to be here and to give this virtual presentation, the webinar today on this topic, to jot it together with Federica. And so just to give you some background regarding where this work is coming from and how we worked on this topic. So it was partly done of my PhD in the last 4 years, but it actually is originating from a larger European project, which is called iTesla, so Innovative Tools for Electric System Security within large within large areas. So that was the European H2020 project, completed in 2017, and then RTE, the French transmission system operator, and we decided to make a follow-up project, and all these amazing collaborators which we list here were involved in over the years in this project, Imperial College, then also colleagues from TU Delft, and then RTE. So that was just the opening credits, and yeah, it's quite exciting to work with this team together. And yeah, now we just quickly introduce some iteration regarding power systems in general. I mean, we have this challenge now to integrate more renewable energy into the system. We have significantly more share of wind power, photovoltaic systems in households, but then also batteries to be integrated. And we generally have this low voltage and then this medium voltage system or grid, and that's all connected to this high voltage system, right? So we have these kind of 3 layers. And this kind of integration challenge of renewable energy is challenging for all 3 different parts of the system. But what we are looking into is the high voltage grid. And there, the major challenge is that it's basically interconnected in, I mean, here you see a really, really large system, right? So you need to think about this kind of systems exist locally, and they are all meshed and integrated in a larger system. So it's a really complex system, and in fact the largest machine, if you want to think about in the world. And yeah, so that's just to quickly say which kind of challenge we have in the power system. And specifically with this research, we're looking into dynamical models or dynamic challenges. So in the past, it was enough to basically check the power balances for static and operate the system in a static way. And now the challenge becomes that the dynamics matter as well, as we have much more fluctuations, as I will outline in the next few slides. But the main thing to understand is that we have this kind of meshed system, which we can abstract as some sort of a graph as well. So we have here, generators, right? So if you look here into these kind of numbers, they illustrate generators. We have a lot of loads, which we call as power negative injections, and power injections are the ones coming from generators. It could be the wind powers and photovoltaic units. And then this is all meshed and integrated. And when we are talking about the dynamic models of the system, so we understand how the physical behavior of the power system works. We understand their, we know Kirchhoff's law, we know all these basic physical models. We can basically reduce the physical model when it comes to dynamics to these kind of 3 variables, which is the phase angle, specifically for each node, right? And then the power, active and reactive power for each of these nodes. And then in terms of nodes, we have also parameters, right? M and D, which describe the dynamics here. So we have one dynamic equation, essentially, which relate all the nodes with each other. And you can think about this as 2 masses who swing together, right? So we have this similar example where basically we have M and D as 2 constants which describe the damping and the swing. And the same thing happens with this in the power system with these generators, where we have M and D which describe this kind of it's a second order ordinary differential equation system, right? Where the phase angle is the time dependency dependent variable, and then we have the P and Q, which we can assume over the time span of seconds, where it's really important to look into in this time scale to be constant, right? So P and Q can be constant. So just to elaborate a bit more what's happening in the system in terms of with respect of these variables which we have. So the first one is the interconnectivity here, like the suspectance matrix, which is a matrix for all of the different nodes, right? A lot of these entries are 0 because we don't have a connection, let's say here in between 13 and 20. Can you see my mouse here if I use that, or?
Yes.
Yes. Yeah, can you see that? Okay, great. Anyway, so the parameters are changing in the system, and there are a few things happening now which were not there when the system was designed 50 years ago and so on. And one of these is that the network itself changes. So the interconnectivity, as you can imagine, it's an interconnected large electricity system spanning Europe, multiple nations. We have changes in the system. So sometimes we have lines disconnected for maintenance purposes. We have sometimes things are disconnected and connected for control actions, for instance. And basically that means that we have discrete changes in system operations, right? So if you think about here, this little example showing two different systems, which, where here's a line first connected, and then another one is this, or like it is essentially a switching, which happens, but it is two discrete changes, right? And that's quite important because it impacts the dynamics quite a lot, and that's why I wanted to point this out to you. But that's not the only thing what changed in the system. So we have also natural power fluctuations, which happen every day. And each of the nodes, we have a very variable power trajectory over the course of hours. For each hour, it looks quite similar, but if you even compare then winter times and summer times, the power profile, which I show here, can be very, very different. So the main message here is we have a lot of variability, and it's a changing system. It changes all the time. But what is really important to maintain as constant all the time is the frequency. And that's really important because it's a design parameter in the power system, which is very important to maintain at all times. And it's basically the control objective which we have to guarantee a reliable system operation. And as you can see here, even there are small fluctuations. The objective is really that to be at 50 Hertz. So really just to quickly summarize these different time scales, we have the frequency, which is kept to be constant. We have the power fluctuations, which is a continuous change, and then we have this kind of discrete changes. And in the time scale of seconds, we can assume that B and P, so the power fluctuations, or the power active and reactive, and also the suspectance matrix, the matrix B, which is basically the interconnectivity of the network, are being constant, right? So the important bit for the dynamical model and the dynamical assessment is the phase angle and the frequency. And now an important part to consider is if things go wrong with the system. As you can imagine, it's a large system. So if a fault happens in any part of the system, it has an immediate impact on all the network. And a fault can be, for example, an outage on a transmission line, or an outage of a generator, or lots of other things. Lots of different equipment can go in outage here. And for example, here illustrated if there's an outage on one of the transmission lines, it basically is this kind of discrete abrupt change happening in the matrix B, right? So suddenly the network is differently connected, which was not planned by the system operator. And that's now the challenge in real-time operation for a system operator who's in charge of maintaining the reliability of the system and to avoid power blackouts, to now somehow react to this change and anticipate to it. And the goal, as said, is to keep the frequency as 50 Hertz, and that's the control objective, as mentioned. So we have a lot of local controllers who now basically follow this kind of signal of the frequency and try to adjust their local power generation or other control actions. So I just wanted to quickly show you an example of that these things happen, right? And here one example was on the 9th of August in the UK, where we experienced a frequency drop, which was because two generators went in, or I think a wind park went in outage at the same time. And what you can see here is this kind of change happens around, I don't know, 4 almost 5 p.m. here, 4:52, and there was some drop, and then after after 2 minutes maybe, the system operator reacted and the frequency recovered, right? So that was a lucky scenario, but I say lucky because actually there were partial blackouts, right? So the tube, for example, in London did not work on this day. So there was some impact. And the question is really, were we just lucky, right? So this time there were 2 very rare events happening at the same time. And maybe they were correlated, maybe they were not. So, but the point is, how can we systematically deal with these cases, right? So question is really, were we just lucky? I mean, could it also go wrong? And if the system is once in a completely blackout, it's extremely hard to restart, right? So we're talking here about a large security risk for society. So yeah, I mean, that's where we are coming from. That's what we work on to avoid these cases. And there's something which is called security assessment, which is in a sense to forecast these states, to forecast if things go wrong in the system, do they lead into a blackout, right? So to answer this kind of question, and it starts all with a forecast of the demand and of generation, right? So we can forecast what we expect in the next few hours, a system operator perspective, let's say. And then basically simulate these cases. So we can say, what would happen if at 5 p.m. tomorrow or in the next few hours a storm is hitting and one of these line or a specific line is getting outage? We can simulate this behavior and so on. And how do we do that? So basically we simulate the time response, right? So it's a similar figure here, but now in green it is an idealistic simulated time response. And you can see here in this case, this frequency recovered, so it's probably expected to went well. And how do we do this kind of assessment? So we formulate the ordinary differential equation system. We put all the equations, and then with standard forward Euler method, we can derive and compute the time response of our phase angles of the entire network. The problem is that this is a very, very slow approach for large systems. So it's not really advisable to do, and system operators don't do that in practice for at least for large systems. And what they are actually only are interested in is this question, whether the state is secure or insecure, right? So it's not really important to be super accurate in the time response. Right, so it's fine to have some deviations here. It's okay as long as you get it right, whether a state in the future is secure or insecure, right? Whether a blackout occurs or a blackout does not occur. So here, as I said, like we allocate, let's say, a label y to this kind of initial condition x. So maybe you can see where I'm going soon is regarding supervised learning approach, right? So we are really just interested in this in this. Question, is the future state secure or insecure? And if it's insecure, then the system operator would adjust. They would anticipate changing some loads, changing generator injections of the system or whatever. It could be anything. And really to make this point again is the core challenge is about the uncertainty what we have in the system operation. So you need to make these security assessments early in advance. And as you can see here, you have a lot of different conditions. And as said, this one is a high dimensional problem, right? So it's really a challenge. This is in large systems, you can have thousands of variables and you need to simulate the combination of multiple uncertainties in each of these variables. So, and the forecast itself is uncertain, right? So you can imagine it's a really complex challenge to analyze everything. And we cannot do that. It's impossible. As system operators. So, and that's where the machine learning approach now comes into play. So our It's not our idea, it's an idea that's actually in development since 20 or 30 years to look into this application. And that's why it's so interesting for us to investigate now again, as we have this boost from machine learning. And the idea is really to avoid time domain simulations, but instead using a classifier to predict the security. So we would like, instead of analyzing all of this data, to basically to filter it to a classifier, right? A binary classifier, because that's the only thing what we are interested in, secure, insecure. If insecure, then we do something about it. If it's secure, we can just ignore this point or this operating conditions. And yeah, that's also where what the rest of the talk is actually about. It's just about how to train and use F, right? So that's what our research is about. And yeah, it's basically this, we formulate this challenge as a supervised learning problem, right? So we have a large database, which we need to create first. And then we learn on this database, and in real-time operation, then we can predict a lot of points. So let me just quickly walk you through this general workflow which we have. And the idea is really to prepare this classifier offline, right? So maybe weeks ahead or months ahead. And instead of simulating everything on the same day, right? That doesn't make sense, but we prepare this classifier properly. Then we can use it in real-time operation. And the key advantage here of this classifier is you can predict points and they have zero computational costs, almost zero, right? Instead of the time domain simulation, which takes a lot of time to carry out. That's the key advantage, and that's the idea what we do. So regarding the workflow, we start essentially to generate some data. So it's not enough to use historical observations. And the main point here to make is historical observations are almost always secure, and you need to generate insecure points as well. So this is part of our work. It's an anti-PhD student who works on this at the moment. Then we need some feature selection and training of this classifier. And then when we have prepared the classifier offline, right? So a few, as I said, weeks, months ahead, we can use it in the online analysis for security assessment and real-time operation. And as I said, like filter all these kind of points and figure out if the power system is leading into some insecure states or not, and based on then anticipate to it and control the system in an appropriate way. So basically the rest of this talk, we focus on this offline part here, but we have a little bit of online as well. So I will very briefly explain you in the next few slides the challenges what we have. I'm not focusing so much on the ideas. Federica is going then a little bit into more depth in the feature selection part. And I will just briefly give you an overview about what we have done in the past in this section here, right, on this part. So I start with data generation, just to give you an idea about how the data looks like. So this is now reducing the system data of the French transmission system, which I can't recall how many nodes it is. It's in the order of 500 to 1,000, I think. But here is really reduced to 2 dimensions only: total wind power and total load. And you can see it's first of all, it's not a trivial dependency pattern, right? So it's not a probability distribution. It's a bit more complex. But then also these green points are secure points and the red points are insecure points, which is very small here to see. So first of all, we realized we have a lot of green points and a few insecure points. As said earlier, there's a large class imbalance, right? So that's the share of positive points, or basically here insecure points in red. And then the second point is that we have some inaccurate predicted points. So here we have already trained the classifier, which is here the pink and the blue points. So I mean, one challenge is this class imbalance which we have. The second challenge is we need to somehow generate artificially, synthetically, new data to move beyond historical observations to create insecure point. The first thing to realize is this is already a challenge to learn a right probabilistic statistical model for that, to then apply Monte-Carlo sampling to it and generate some new points. And one challenge is here this kind of complex dependency pattern, which are, as I said, non-trivial, as in this example. So let's move forward regarding the classifier and how we can prepare such a classifier. So what is different to yeah, now we at the moment we are rethinking this a little bit, but what is very important to realize in the last 20 or 30 years, people have really focused on decision trees. And that is because we are talking about a very safety critical task, and the human is here also in the loop, right? So it's all about this trust, to trust an algorithm, to trust a machine learning approach. And that's why it's so important to look into this interpretability, and the decision trees is still the model of choice, I would say, in a lot of publications, even in the last few years. And also in our project, it was the model we are focused on. And there, yeah, these kind of balance trees are the most interpretable for human to understand. So that's what the target is, to learn very simple rules. But there are some other challenges just to get there. And it has all to do with this, with the predictions that they can be wrong, right? So and the origin of that is that we cannot exactly match. We cannot exactly match this the real security limit, right? So we learn this classifier, which is the blue one, but it may be inaccurate at some point. So there may be some wrong points, and yeah, the actual security limit could look a little different. And what's important to point out that we have not only this cost imbalance, but we have also cost sensitivity, as it's, yeah, I mean, probably you're familiar with this table, but it's essentially we have two different types of errors, right? One is the missed alarms and the false alarms. And to miss an alarm is it's very, very bad. It's basically you're missing a potential power blackout, right? So even if these security rules or the decision trees would be used in practice, which are not yet there, it would be very bad to miss one of these alarms. It's when we are basically, we think an operating condition, if all some data, real-time data, the system is secure, but actually it is insecure, and we don't know that, we cannot spot that. And that's a problem. And this cost sensitivity is exactly about that we have not the same cost related to to false prediction, false alarm and missed alarms, right? So that's this kind of cost skewness which we have in the learning problem. And what can we do about it? We, for example, use now a probabilistic way of learning classifiers. So it's basically to compute probabilities as outputs from classifiers instead of just the binary labels y equals 0 or y equal 1. But we also compute probability estimates essentially based on scores, but we cannot use directly scores from decision trees, as here, for example, which is just the share of training data of positive or negative data here in the decision tree. But we need to do some calibration because we have this natural distortion, which is which basically was presented by Platt, Professor Platt, and we need to do some fitting of a sigmoid function to basically calibrate our probability curve to that. So that's what we investigated in the past. We also investigated to select the right model using our C-curve. And that's essentially another way of addressing this kind of class this kind of cost sensitivity, right? So you select the cost optimal curve. So here we see 4 different classifiers, right? And we would like to select the classifier which is in this top left corner. That would mean 100% accuracy, 0% inaccuracy. And basically these 2 axes are about which kind of class you, in your trade-off curve, let's call it, of your classifier, or your operating curve from the classifier, is what's your trade-off in terms of making missed alarms or false alarms? Which kind of error is preferable? And the cost optimal choice is this kind of Z star here, which we marked. And you can compute that with taking the probability of contingency. So contingency here means this failure, which I am referencing to, right? So failure of an equipment. But basically with this equation, you easily can compute where the cost optimal point is, and then making the selection for which security rule or which decision tree to choose. And then just applying this threshold that to on the probability output of the classifier to predict either it's secure or insecure. We also investigated cost curves in the past, which is another method to directly, so the RLC curve is basically to use just a single point here on your curve, right? So, these things, the probability of contingency A can change, right? So it's not static, so this can change, but also the impact of contingency can change. So these are all estimates. This means that we do not actually select a classifier based on a single point, but we have an area which matters, and this cost curve is specifically now computing, or can be used to compute the expected cost, and cost here really means load shedding, right? So this means we have a partial power blackout in some sense, and then we would see, for example, to select here this green decision tree, because we are considering here an interval, which is important, and you can see that over the interval, the green one is quite close to the best one, which is possible, this brown one. But the brown one has quite a lot of nodes in the decision tree, so it's a large structure, whereas the green one has a nice trade-off. It's still interpretable in terms of the number of nodes. So that's how you can how we used it. And just to give you another look at this approach and to give you some intuition about why the machine learning approach is promising. So if you look here into just to simulate a single data point, right? So this means one operating condition. It takes for this French transmission system here 57 seconds, which is quite a lot to just generate a single data point. So this means it's super important to generate the right data and to use machine learning approaches which just require a little amount of data, right? So that's also important. And we just made here in one work of ours just some small changes. We changed the type of model we use. We formulated a different decision tree, which is a bit more interpretable, a bit more, has some other assumptions. And we reduced the data by, I don't know what this is, maybe 75% or something like that. And that was just a small change, but it made a huge difference for the learning problem. And that's at the moment what we are looking to either improve it incrementally, but also now we're investigating much more fundamental changes. And I'm handing over to Federica, who's explaining you a little bit more into depth what we are also doing, which is feature selection and fitting into this offline workflow.
Yeah. Okay, so now we move on the next step of the offline stage, and we will focus on feature selection at the moment. Okay. And first of all, I would like to describe better why the main motivation of using feature selection in dynamics in security assessment workflow. So let's assume we have a first system, that is system 1, and we have the relationship between the data and the security label Y given by the function GB1. So the idea of using machine learning is to approximate this relationship by a classifier, FP1, for which the difference between the true label, security label Y, and the predicted label Y tilde is minimized. Now let's assume that we move to a new system, so there is a change in the system, and we move to system 2. And in this case, we have a different relationship between the data X and the security label. However, we still use the same offline training classifier FP1. And FP1 may not work for the second system. And this means that the difference between the predicted label and the true label is not minimized. Let's try to understand why system changes is a crucial problem in modern power system operations. So as Jochen already said, power injection are becoming more dynamic due to integration of renewable energy sources, and operation is also changing. However, the control objectives of the operators is always the same, that is keep the system frequency at 50 Hz. So now what is happening is that the power injection are more dynamic, and at the same time, the operation from operators is different. So what we can have like unforeseen outages, but operators can also decide to change the topology as a control action to adjust like the injection of the power. So this means that system changes are becoming very frequent in modern power system. Ideally, we would like to have a classifier which is able to generalize to all possible topology changes. So a classifier FR, which works for GB1, but also for GB2 and for all the possible matrix B that we can have in the system. But due to the high dimensionality of the problem, this is not feasible. So what we try to do is to understand and identify the subset of features which best capture the security condition, then try to train the classifier on these features in such a way that is more robust against the topology changes. However, in our system, the security is strictly related to the system physics. So what we need to look for is a new feature selection approach, which is able to consider both the data, but also the changes in the system. So this means that even if we have like a fault in the system, the identified variables that are with the red circle in the figure are still contain some relevant information regarding the security of the system. Okay, and this is the new feature selection approach that we propose. It's based on a graphical model of the system. So in this model, each node is associated to a voltage measurement and represent a voltage variable. And the links are the statistical dependency between the voltage variables. And we use the mutual information as metric. This graphical model can be described by a joint probability distribution. And this joint probability distribution can be modeled by a particular Bayesian network that is called the three-augmented naive Bayes model. In this model, we have that each variable has as parent another variable and the security label Y. And this model allows us to identify an approximation of the Markov-Blanket of the security label Y, where for Markov-Blanket, we define the subset of features which is more relevant to the security label itself. And this is how we select the most relevant features to the security label. Now we use this feature selection both in the offline stage, but also in a new stage between offline and online stage. The objective of this new stage is to update the training database by including some more recent information about the next operating state, and to retrain a new classifier that is more accurate on the next operating stage. However, this stage is performed very close to real-time operation. So this means that we need to be as fast as possible, and the use of the feature selection approach we are proposing allows us to speed the training process. Okay, let's test now the feature selection approach. We have a standard, we have a case study on a standard system composed by 6 buses. And in this figure here, we are comparing our approach, that is the green one, with existing feature selection approaches. Generally, you can say that feature selection approaches can be classified into two classes. So we have the filter methods and the wrapper methods. The first one are very fast, but they result in low accuracies. And the second one are usually very accurate, but the problem is that the computational cost is very high. So as we can see from this plot, our approach, that is the green one, is able to achieve the same accuracy of the wrapper method, that is the sequential feature selector, the red one, but the computational time is strongly reduced, and it's very similar to the filter approach. So this means that our approach results in the best trade-off between accuracy and computational times, and for this reason, it is the most suitable one for the nearest time stage, where we need high accuracy, but we also need to be very fast. Okay, and now we test the computational savings by applying the proposed 3-stage workflow with the update of the classifier. The use of the feature selection approach in the nearer time stage allows to reduce the training database size by almost 60%, achieving the same accuracy that we had with the full training database size. And we can see that the computational time compared to the wrapper method is reduced. And then we perform the same analysis for the offline stage. And in the offline stage, we can reduce the training database size up to 95%. And this is mainly because now we have a new stage in which we periodically include the new data in the training database. Okay, now looking at the table, we can see that the use of the feature selection approach in the offline stage allows to reduce the simulation time by from 40 minutes to 10 minutes. And we need to say that simulating the data is the most expensive in terms of task, in terms of computational cost in this kind of workflow. So reducing the time of a simulation, it's very important. And we also show in this table the time for the feature selection, the time to train the classifier. And finally, we can see that using the proposed feature selection approach in real-time, in offline and real-time stage allows to reduce the total computational cost of the overall workflow by up to 75%. Okay, another idea would be to identify those topology changes that really impact on the performance, on the accuracy performance of the classifier. So this means that a classifier that is trained offline may still work on a new topology, even if the system has changed. So what we would like to do is to define a new metric that can be computed in real-time operations. So this means that it cannot involve time domain simulations because we do not have real-time operation time to perform time domain simulations. So the metric we are looking for is just based on data and not on security labels that we need to simulate. So a proper threshold is validated for this metric offline. Then the metric is evaluated in real-time operation on the new data. If the metric is higher than the threshold, this means that a new classifier is needed. Otherwise, the old classifier can be still used even if the topology is changed. The metric is based on convex hull. As you can see, we use decision tree as classifiers. So each data ends up in a terminal node, in a leaf node of the decision tree, and each node corresponds to a secure or insecure region. Now, for each terminal node of the decision tree, we construct two different convex hulls. One for data ending up in that terminal node before the topology change, and another one for data ending up in the same terminal node after the topology change. And then we just compare these two convex hulls by evaluating the Hausdorff distance between these two convex hulls. So the Hausdorff difference between, for example, the set B2 and set B1 is the greatest distance of B2 to the nearest point in the set B1. And this is the definition of the Hausdorff distance. And the final metric is just the mean value of the Hausdorff distance over all the leaf nodes. Okay, after the detection of high impact topological change, now we need to construct a new training database and then train a new classifier. However, we are still in real-time operation, so we do not have enough time to simulate a vast number of new data. So what we do is to take advantage of the knowledge included in the offline training database. And that's here the idea. So we construct two convex hulls, one for the data before the topology change, B1, and another one, B2, for the data after the topology change. And in the new training database, we are going to include the points of B1 that are still relevant for the new topology. So this point in the intersection of B1 and B2. And we also include, and this is the first points we are going to include. And then we just include the points of B2 that are not included to B1, so that are not relevant to the old topology. So what this means is that we don't need to simulate all the points in B2, but just the points that are not included in B1. And this allows to reduce the number of simulation to perform in real-time operation. Okay, now we test the approach. So we first of all tune the map. In this case, we also have a case study on the 6/8 bus system. We first of all tune the metric. So we have 42 different topology changes. So on the x-axis, we have 42 different topology changes that are according to increasing value of the accuracy. And we can see that for increasing value of the accuracy, the metric is decreasing. So this means that offline, we can set a threshold of the accuracy at 95%, corresponding to a metric value of 0.9. And then in real-time operation, we compute the metric for the new data. If the metric is higher than 0.9, this means that we need a new classifier. Otherwise, the old classifier can be still used for the new topology. And this metric allows to reduce the number of new training up to 60%. Okay, after the metric, the tuning of the metric and the detection of high impact topological changes, now we need to construct the new databases. So in this table, we have three different approaches. In the first approach, we just consider all the old data and the new data. In the second approach, we perform the selection just for the old data, so just the red points and we consider all the data in V2. And in the last approach, in this case, we do the selection for the new data and for the old data. And we can see that by using our approach, that is the last one, the accuracy is not deteriorated, but we reduce the time for simulation by 55%. Finally, we test the performance of the overall workflow, so the 3 stages workflow with the metric and the selection for the training database. In this case, we compare it against the traditional approaches for security assessment. So the first approach is just the 2 stages approach, in which we have an offline training database classifier, and we use this classifier in real-time operation irrespective of topology changes. In the second approach, we in this case update the classifier in a near real-time stage periodically. However, the updates are completely random. So if we are lucky, we are able to detect all the eigenpart topological changes. Otherwise, we do not detect them. And finally, there is the third approach is our approach, in which we use the metric in the real-time stage, and then we also construct the training database. And the last approach is just given as an upper limit. In this case, we are saying that a new classifier is training after each topological change or by simulating all the new data. However, this approach is not feasible as I say, topology changes are becoming very frequent, so it's not possible to always train a new classifier. And as we can see from the accuracy performance, our approach is able to improve the accuracy compared to the traditional approaches by almost 10%. And this accuracy is also higher than the last approach. And this means that the offline database contains relevant information regarding the new topologies. Okay, now we move on the next step, so the online stage. And
yeah. All right, thanks. Yeah, so just to wrap up from for this talk, so we want to show you as well how we use it, the classifier in the online analysis. So when it's coming to online analysis, basically we have the option to also run some simulations. So it's not only we have the option of having a combined approach. So to use machine learning supervised learning with more the conventional approaches, right? So how we best would combine them, we would first run all the data through the classifiers using now this probabilistic output, what we showed you earlier. And computing some sort of risk, confidence, for instance, how confident the classifier is about their prediction or this probability. And then using the standard simulator, so the numerical integration method, to simulate the most risky points afterwards. So it's basically this kind of combination or sequential approach. And you just use the ones which have the highest risk, in essence, then here with marked in red, to carry out then simulations, and that was then improving our final results. Hopefully, you can compute this risk with just taking the probabilistic output of the classifier, right? So the score, which we showed you, multiplying now, computing the risk. Basically, the risk is the computation of the probability times the impact, right? So that's the risk function, very specific or like very generic defined, and the impact here, or the is the cost of if a blackout occurs, or the cost of taking a control measure into place in system operations, so CFN. So we have this risk formula for secure. If you predict the point secure as secure, and we can also compute the risk of predicting the operating condition XY as insecure. And there we have the impact of contingency, not here, sorry. And then we would compare these two risks before we make the decision, before our algorithm makes the decision. If you predict an operating condition as secure or insecure, you compute these two risks, you compare them, and you predict the ones which have the lowest risk. And then afterwards, as said, you would run on the high risk points these kind of simulations afterwards. And I also have some case study here from a very small system, just 6 buses, but still the point, yeah, the idea gets illustrated, I would say. So we have inaccurate predictions, like showing here with the number of simulations. So let's say here on this side of the figure with 100% simulation, it means we simulate all the data, right, with our numerical integrator. And on the left side, 0% means we just rely on the classifier. So this we compare here 3 different approaches. When we use no machine learning, basically we don't have a classifier to rely on. It means that we use a random generator to say whether I assign this as 0 or as 1, as secure and insecure. So as you can see, linearly, the inaccurate predictions of assignments, not predictions, are it's linearly decreasing, and so as does the risk. But if we look into a standard classifier, you note already that if we use a classifier to predict secure, or the label secure and insecure, we have a reduction of 1 order of magnitude already, which is here on the left side, I said, using only machine learning, and here then some and here we aim actually to isolate and to find these 15 cases, which are missed and false alarms. But as we have not an advanced approach to find these, it is not really fast decreasing. So we basically still need to simulate all the data, right, to identify these 15 cases. However, with the proposed approach, when you use this risk output of the classifier, or the probabilistic output of the classifier, it reduces immediately in just a few. I think these are like 50 or 40 to 50 simulations. You identified all the 15 cases which were inaccurately predicted inaccurately predicted at the, if you only rely on classifiers. So it's basically an overall and computational savings of 95%. When you rely on classifiers. And the important thing is to point out, that's also what we pointed out to our collaborators at RTE, the French TSO, is you still have 0 risks, right? So you still have, even if you, so basically what they would do at the moment is to carry out all the simulations at this point. So, and you can only be better than that, right? So it's even if you have the worst classifier trained, you are always better than the normal approach. So that's the main message here. We have also some other, just one slide to show you on the control approaches. So it's in terms of when you identify an insecure point, what you do. And we derived some approaches where we implement the structure of this decision tree with an optimization problems, because optimization problem is the standard tool being used, or the standard approach being used to make operating decisions, control operating decisions. So we try to use the same kind of tree structure for these security rules to implement into an optimization problem. But we don't want to present that today, as we have some other exciting things to show you before, hopefully exciting. But yeah, if you are more interested, you are welcome to contact or read about our work. But just quickly to conclude, basically with our presentation, what we aim to do is to raise a bit the awareness that the problem we are working on is very safety critical and an important application to look into. Because as said at the beginning, these power blackouts, as we move to net zero targets, right? So we have to get rid of all the gas and oil production plants. We need to implement more renewables. It is a really, really large challenge for system operators to operate in a secure way and to avoid these power blackouts. Even though they have not been there in the past, they may occur in the future. And our job is that they don't occur, right? So it's to work on this kind of rare extreme cases, high impact, low probability events. And that's what makes this work so exciting from my viewpoint. And supervised learning, as said, is a promising set of methods, and it's this application, the methods are important because actually the ideas are around since 30 years, right? So I said at the beginning, but now we have this boost of machine learning approaches, machine learning methods, that it's kind of a next evolution, how we see it, and specifically with this integration. I said here, basically the integration of these physical models, which was done in the past, but then also with machine learning and specifically with deep learning approaches together is a very promising approach here, because in this area of research, we know the dynamics, right? So we know the physical equations, we know the swing equations, which we showed you earlier. And that's what makes it so exciting. And that's also where we focus on our future work, it's basically a couple of projects or ideas which are around and which we started to work on and which we plan to work on. It's essentially how you integrate solvers in deep learning frameworks, right? So how to use backpropagation through and joint sensitivities, etc., from solvers for ODEs. Essentially, how you capture the structure of the power system within graph neural networks, right? I think that's what Haiwa is now working, as far as I know, a little bit as well. And then differential optimization, so how you use these standard control approaches, also in backpropagation way to implement them in these approaches, in deep learning approaches, and then to design basically end-to-end workflows. We have some initial starting points in this direction. And overall, this is also where we see the research heading. Where we are interested in is basically to look more into this data-driven scientific computing and focusing on the application, which we try to illustrate today to you. With that, I hoped maybe some of you have some questions. Thank you very much for your attention.
Thank you. Thank you very much, both to Jochen and also to Federica for the presentation. So we can open now for questions. If you have a question, maybe raise first your hand, but then you can unmute yourself and then ask the question directly.
I have a question. So you remember you can to identify the risk of predicting the security status, right? So if that can be further used in operation, in control framework, the risk, I mean, how we use that identified risk.
I can show you something here. So regarding this, so how we use the identified risk. So basically, when we use so each of these nodes, basically in the control framework, we have the feasible region of the optimization problem, and we have some control actions which we possibly can carry out, and we basically each of these node carry a risk, right? So if the operating condition falls into this node, right? So here in node 3, it's basically a larger risk because it's a node where the training data is partly secure and partly insecure. Whereas when it falls into another node, for example, here in N4, it is purely secure, here illustrated with the green color. Yeah. So that means that you would formulate the optimization problem to derive some control actions in such a way that the N4, the green node, is preferable, right? So you can implement this either in the objective function to say we would move, or we try to minimize the risk associated with different nodes, let's say as a disjunctive formulation. So you have basically the optimizer, or the optimization problem looks like you have different discrete sets, and each discrete set is one of the nodes. And yeah, if each of these nodes has like this kind of risk associated to it, you can basically formulate this as a sum in your objective function and minimizing the that your operating condition is falling into the node with the lowest risk, with the green here, for example, here with N4.
So
does that make sense slightly? I mean, this is what we show here with the summation over y. So y here stands for a binary variable for each of these 3 different nodes.
So the model, the machine learning model, is trained before we put this risk into the optimization problem.
Yes.
Okay, I see. Thanks.
Yeah. Cheers. Thank you.
Really cool.
Thank you. Are there any further questions? There was a question in the chat. It's from Iraj Ahangari. I've got a question about unbalanced data in practice. Most of the time we are in stable state and we have a few shutdowns or blackout state. How can we overcome this challenge? Maybe you can mention or describe a bit more the data generation that you were performing.
Mm-hmm. Yeah, exactly. So that's a huge challenge regarding to overcome that. So basically regarding data generation, we have 3 different approaches which we looked into. So the first one is where we start with historical observations and we train this statistical model, right? And then we apply, when we have trained the statistical model, so we describe this with, let's say, a Copula model, a multivariate Gaussian distribution. We can generate similar points to the historical observations, but that's not what we want, right? So it's not ideal. So what we want is this kind of insecure points, which are different. So there are methods which are coming from extreme rare event sampling, right? So which are basically sampling in the tail of the probability distribution instead of in the generating a lot of points in the, let's say, in the mean, but a lot of points in the tails. So we looked into that. But then we have also the second approach, which is what we call generic sampling. And that means that we ignore everything what happened in the past. We don't start to sample anything from the historical observations. So no statistics based and no probability distributions. So we start basically with the feasible conditions. So we basically go first principles, and your model, right, or your power system can be operated in multiple ways, with multiple dimensions of freedom, right? So with multiple, variables which are free, and we just try to generate points which are in this feasible region to generate a very random cloud, and that's the completely opposite approach, which is also not ideal, because you generate points which are unrealistic, which never occur in real operation. At the same point, you have no control about this how many secure or insecure points you generate, and it's very inefficient. So the third approach which we use is active learning. So active learning is an approach where we first train a classifier on historical observations, and you maybe have a few insecure points and a lot of secure points. And then when you have learned the first classifier, you can basically pass new generated data, because what is the cost, computationally costly, is to generate the label. It's not costly to generate X, it's costly to generate Y. So you generate a lot of X, then you pass them through the classifier, and where the confidence is the least, these are the points which are interesting to evaluate and to generate the label, right? So that means that active learning is essentially a concept to do this in a loop, to train a classifier, pass new data through, select a few ones, analyze them, compute the label, learn a new classifier in the next loop, which is now improved and better, pass again new data through, and so on and so forth. So that's a way of indirectly generate more insecure points, because you would assume that the insecure, even if you don't know the label yet, the ones which are likely to be insecure are the ones which your active learning concept is identifying, right? So that's the third way of approaching. And very excitingly, at the moment, we are the next step of of Alamin, our collaborator, our PhD student at Imperial College at the moment, is about combining these 3 together. Well, because that would be the ideal concept, but it's really, really hard. And yeah, it's still an open question. If there are other approaches from other research areas, I would be super happy to have a conversation. So if there's any other ideas, I would be super happy about that, to brainstorm together. Or thanks for the question.
Thank you for the answer. So I think we are punctual at time, but maybe a very last question concerning the interpretability, because you mentioned that you decided to go in the direction of decision trees because of the interpretability. So did you discuss the models then with the domain experts, or were they really able to interpret them, and were they happy with the results? And, so what was the feedback that you got on the interpretability, and which level of interpretability were you able to achieve?
Federica, do you want to do it, or should I?
We have an external collaborator that is the French transmission operator, and at the moment, I mean, the use of machine learning in current operation is not so common. So the idea is to use, was their idea to use like the simple classifier, because they need to understand what to do if something goes wrong. So they were quite happy about using decision trees. However, during the last meeting, so now we're thinking about to use more complicated models, and that's why we are looking into now deep learning models and neural networks in general. However, at the moment, if you look to the operation, the current operation in the like European system transmission system operators, the use of machine learning is not very common. So the first step should be decision tree, and then after that we can maybe test other approaches.
Yeah.
Okay, thank you also for this answer. Is there any other urgent question that we should answer before a weekend? There are no further questions, so thank you very much once again to both of you, but also to everyone for joining and for asking the questions and for staying all the way through. So we are excited about your research directions and to see the updates of these results. Thank you very much, and enjoy the evening.
Thank you.
Thanks everyone, and thanks for having me or having us. Thanks for the invitation again.
Thanks very much for the invitation.